Okay, so it's Module 10 time, and Module 10 deals with chapters 13 and 14 in your book, the topic being light. And one thing that I want you to keep in really the forefront of your mind the entire time you go through these chapters is to realize that when we say light, we are not just talking about visible light. It turns out, that's commonplace. That's when we talk about light, we think about visible light. In fact, that's why you can see me right now is because these lights in this room are producing visible light. That visible light is hitting me, bouncing off me, and being collected by the camera. But it turns out that visible light is just a little smidgen of all the possible electromagnetic radiation that's out there. So that's one thing to keep in mind. So when we say light in physics, we're not just talking about the visible spectrum. We're talking about all electromagnetic waves. In fact, what I want you to do is to find a remote control kicking around the house and press the on button and look at it. And it turns out you're not going to see anything. When you press that button, it's not going to look any different than when it's on or off. But try an iPad, try a digital camera, do the same thing. What do you see now? Do you see the light? Turns out your eye can't see that. When I look at this, I see nothing. When I point it to the camera, I see flashes. That's because this is not producing visible light. It's producing, it turns out, infrared light. And not only can we see it, we can actually hear it. I'm going to show you a little apparatus, and I know it's going to look all kinds of fancy. It's got all kinds of wires and stuff, but all it really is just a photocell. Here's my photocell, and it's attached to a speaker. So what's going to happen is this photocell is going to pick up light and create a signal, and it's going to amplify that small signal and create a noise. And so, in fact, I can prove that by, notice when I cover my photocell, you hear less background noise, don't you? Now let me hit it with my remote control. Ready? Hear that? You're actually hearing light. Isn't that pretty awesome? So again, keep that in mind through the entire module. Keep in mind the fact that light is not just a small little visible spectrum. When we talk about light in physics, it's all of the electromagnetic wave spectrum. Okay, I'm going to try to keep my comments as brief as possible during this module because there's a lot of video content in this module, and that's going to take up a lot of time. So one thing I do want to mention, however, right at the outset is that light is similar to sound, but different than sound. Light does travel in waves, just like sound does. However, light does not need a medium to travel through. Light can move through empty space. In fact, that's how it gets from the Earth, from the sun to the Earth. It travels through essentially the vacuum that is empty space quite easily, even though sound waves couldn't travel through that same vacuum of empty space, because sound waves need a medium to travel through. Light does not need a medium to travel through. How fast does light travel? It moves much, much faster than sound does. Light travels at a speed of 3 times 10 to the 8th meters per second. That means 300 million meters per second, which may not mean a whole lot to you, so I'll try to put it in more graspable terms. The speed of light is 186,000 miles per second. 186,000 miles per second. That's how fast light travels. So what does that mean? Because that's still a pretty big number. Remember the Earth? Yeah, you should probably know the Earth pretty well. The Earth's circumference, means the distance around it, is 25,000 miles. So therefore, a ray of light could go around the Earth not once, not twice, not 3 times, not 4 times, not 5 times, not 6 times, not 7, actually just over 7 times is how far a ray of light would travel in 1 second going at the speed of light. And again, this is not just visible light we're talking about. When we talk about light in physics, we're talking about the entire electromagnetic spectrum. If you learn nothing else out of this module, I hope you at least take away the lesson that, or maybe your eyes will be open to the fact that human vision kind of stinks, because all we can see is this small sliver of wavelengths in this entire range of electromagnetic radiation. So we only experience a small amount of what's out there. Now, what you'll notice in this graph is that they give you the names of these different types of light: infrared light, microwaves, et cetera, et cetera. The wavelengths increase in this direction. So they increase to the right for wavelengths. Of course, wavelength and frequency, as you learned, are inverses to each other. So therefore, if the wavelengths are increasing to the right, then your frequencies are increasing to the left, and that's what you see as far as some of those numbers. Notice that the exponents get much larger. And it turns out that higher frequency light has more energy, and that's why X-rays, gamma rays, ultraviolet, we want to limit our exposure to those things because of the energy and the penetrating power of those types of light can do damage to our cells and to our DNA. That's where you get the threat of cancer and stuff when you have too much dosage of gamma rays, X-rays, ultraviolet, that sort of stuff. But what we see here is that the human eye, well, we're not even as good as some cats and some other animals actually see more of a range of frequencies than we do. But the human eye is relatively limited in what it can experience.
So here's a little experiment you can actually do on your own. You don't need fancy equipment. I've got some special equipment here, but you could actually just use a light bulb and any object that's going to block the light. So what I've got is I've got a light source, that's the black thing on the left, and then I've got a little box that has looks like it's transparent, but it's actually opaque on the side that's facing the light source. And so what we're going to wind up creating is a shadow. And the main purpose of this experiment is to show you that light does indeed travel in straight lines, and that you can actually trace the lines of light, what we call rays. And that becomes very important, as you're going to find out in this module, when you get into the activities involving mirrors and lenses and that sort of stuff. So first of all, let me turn on my light source. You'll see kind of what we're going to expect to see. And then I'm going to turn on my light, the overhead lights at least, and make it show up a little bit better. So what you see is the light source is indeed producing light, and that light is being blocked by my transparent, or my box. And that winds up casting a shadow. And the cool thing is you can actually change then the location of kind of the target. I'm going to move the box a little farther back, and notice what happens to the shadow. It should look a little different. Okay, so the first thing I'm going to do is I'm going to outline my little light source here. I'm going to do it in green. This is mainly just so I'll be able to put in another photo and have it align pretty well. Next thing I'm going to do is I'm going to now outline the shadow that's cast by my box as best I can. And if I were doing this on paper, I'd have a ruler out and all that kind of stuff. I'm just going to freehand this and get essentially the general shape of the shadow that is created. Notice that I've now superimposed the other photo where I've changed the position of the box. I moved a little farther away from the source, and notice the shape of the shadow is different. And now what I can do is I can actually trace those rays back approximately. And we see that indeed light does travel in straight lines, and that as we move our object farther away, it winds up creating a smaller shadow than when the object is close to the light source. So this time I've got a beam of light that is hitting a plane mirror. I've got my plane mirror in the middle of this little disc here. And I'm going to turn off the light. And I want you to pay attention to what happens when, right now the beam is being reflected straight back to the light source. But notice what happens when I start to move my light source. The light winds up hitting the mirror. And notice that the beam of light, which are essentially a bunch of parallel rays, wind up bouncing off the mirror and being reflected as a beam of light. Now instead of a wide beam of light, I've actually narrowed down the beam into essentially one ray. I've put a little slit in front of the light source, and that has narrowed my beam. I'm going to show that off a little bit better by turning off the light. So notice that again, the light is hitting my plane mirror and bouncing straight back into the light source. But as I change the angle, notice what happens. Now you can't see the numbers on my little disc there. What should be pretty clear is that the angle of what's called incidence is equal to the angle of reflection. Here's a neat little demonstration that deals with the images formed by a plane mirror. So what we have here is a light source that's producing two beams of light, and they are slightly divergent. The light source is actually the light is diverging as it hits the mirror. And I'm going to turn off the light now, the overhead light, and you can see a little better as far as what those rays wind up looking like. Now I want you to see what happens as I start to rotate this, because right now essentially the light source is pointed right at the mirror. But as I rotate the light source and we see these beams bounce off the mirror, we're going to do a little bit of ray tracing, which will allow us to see where the image, if you were viewing, instead of, if you were looking at the mirror, not looking directly at the light source, but actually looking at its reflection, the question is, where would that image appear to be originating from? Okay, so we're talking about plane mirrors and the reflection off of a plane mirror. I'm first of all going to remind you of the position of this plane mirror. I'm going to draw it there in red. That's essentially where the mirror is. So notice that these light rays are coming from a source and are bouncing off of the mirror and reflecting. Now what we can do is we can actually trace those rays. I can actually kind of trace the rays, the reflected rays, onto the other side of the mirror and essentially come up with the position of my image. In a similar way, I can, and I'll do it in blue, trace the rays that are coming from my source backward and find the position of my source. And what we wind up finding is that the position of the source with respect to the mirror, the distance here from the object or the source to the mirror, is the same as the distance from the mirror to my image. Okay, so this time, instead of having a plane mirror, we have what's called a concave mirror. Notice that this mirror has a bend to it, slightly bent, and I've got a light source that's producing two beams of light. Turn the overhead lights out and you can see that a little bit better. And what you'll also notice is that when the beams of light hit the concave mirror, they converge. In fact, what I can also do is I can change the little cover here. And instead of having two beams of light, I can actually create four beams of light, just so that you can see that the light bends different amounts depending upon what part of the mirror it is striking. When we start dealing with lenses and mirrors, we need to learn some jargon. So one thing you have to notice is that the parallel rays of light that hit the mirror all seem to converge on a point. And that point is what's called the focal point. And it's usually labeled with an F. Now the distance between the focal point and the center of the mirror is something called the focal length. Now notice that the mirror itself, I'm going to try to draw the curvature of the mirror here in red, kind of looks like one part of a big old circle, correct? Well, it turns out that the center of curvature, if we actually completed the circle, we would wind up with a center of the circle here, where I'm putting my little red dot. Turns out that is twice the distance from the mirror as the focal point is. So essentially this length from the red dot to the mirror is 2f. Now another thing that I can do is I can actually change the curvature of the mirror. I'm going to try this. I'm going to try to make it a little less bent, and we can see what impact that has on the light rays. Notice they're converging to a point. Let's see what happens when I make it a little less bent as far as the point where the light rays converge. And I can also make it a little more bent. I can increase the bend, and if I can get the mirror to bend equally as I bend this thing, so I'm bending it a little more, and notice that the rays converge a little differently. This time what I've done is I've changed the curvature of the mirror. Instead of having a concave mirror, I've got what's called a convex mirror. So it's bent the other way. And we'll see what happens when we have a light source hitting a convex mirror. So notice that my two beams of light hit the mirror and reflect. In this case, they reflect outward. I can also show this with my force slit. Okay, so one thing you'll notice is that the convex mirror behaves differently than a concave mirror. You'll notice that the rays that hit the mirror don't converge, rather they are divergent. They reflect kind of spreading away from each other. But if we lengthen these rays behind the mirror, notice they do seem to converge and create an intersection point. That is the focal length. So they wind up creating a virtual focus behind the mirror, and that distance from the mirror to that point, the focal point, is what's called the focal length. And again, notice that this mirror is curved, kind of looks like a big old circle. The center of curvature is twice the distance from the mirror.
Just to make this a little more clear, what you're looking at here is actually a telescope. It's not a telescope we usually think about. When we think about telescopes, quite often we're thinking about visible light telescopes, which is what you use in your backyard and that sort of thing. This is a radio telescope. Remember the difference between radio waves and, say, visible light waves. Radio waves have much longer wavelengths. And so a visible light, I'm going to draw this in kind of a light blue. Visible light has a tiny little, and of course I'm exaggerating here, tiny little wavelength. And therefore most of it is either going to pass completely through this open mesh screen, or it might hit one of these metal bars and bounce in this direction or that direction. Notice it's a diffuse reflector, as opposed to, I'll do my radio waves in red. Radio waves being much longer, it's going to essentially act like they're so large that even though the mesh is open, these radio waves don't see those open areas. They're going to get these radio waves are going to reflect, and this is going to essentially act like a nice smooth mirror. And we know what happens with mirrors, a curved mirror like this, that the incident light gets reflected to the focal point. And so no matter where the radio wave hits, it's going to be reflected, just like it would off of a smooth mirror, boom, to that focal point. And that's where the signal is amplified, and then you can analyze the radio information. Okay, so road surfaces really aren't truly smooth. They're full of all kinds of nooks and crannies, and that's good for traction, but it's also good for your visibility. So what happens is when you've got your headlights on, of course the road doesn't, this is of course at night, the road doesn't produce its own light. It only can reflect light. And so your light comes in, of course your light's coming in all directions from your headlights, and it hits the rough road surface, and some of it gets, of course it can scatter in all directions, but some of it gets scattered back in your direction, so you can actually see that surface. However, what happens on a rainy night when the road surface is wet? Notice that essentially you get a layer of water that fills in all those nooks and crannies. And therefore, the light now is going to not be a diffuse reflector, or the surface is not going to be a diffuse reflector, rather it's going to be a smooth reflector. And therefore that light's going to go bouncing off into space, but not back toward your car. and therefore that light that you're shining on the road does nothing as far as helping you see the road any better. In a similar way, fog can be a problem. Why is that? Because fog, another reason why we see things is because there's contrast. In this particular diagram or this image, I created this back in my USA Today days. You can see a deer at night. Why? Because you're on a clear night, your headlights throw light out there and hits the deer and it bounces back and you see the deer. And then of course, outside of the deer, you're seeing nothing. So there's a good amount of contrast. However, when there's fog, the problem is that your headlights shoot light out and that light is almost immediately being turned around, scattered back to you. And therefore, you have no contrast. You're getting all this light back at you and there's no way of being able to pick out objects because you're essentially not getting any contrast.
Okay, so we're talking about colors. What I've got here is I've got a piece of black cardboard or construction paper. And when I say black, as you'll notice, this is not a perfectly black surface because we are getting a certain amount of light reflected from the black construction paper. So it's not, so it is, we are getting some light bouncing back. In a perfectly black surface, we would have light that's hitting the surface and being completely absorbed with nothing being reflected. So we're going to take black with a grain of salt here. But what we have is light here in the room, white light, that is hitting the black construction paper, and some of it is being reflected into our eyes. You'll notice there's two words on there. They both say test. One is written in red crayon, one is written in blue crayon. And so from those parts of the paper, what we can tell is that all the different colors of light are hitting those areas that say test. But most of the colors are being absorbed with the exception of red in the top case. Notice the red light is being reflected off of those crayon areas and bouncing back into the camera or into our eyes. And for the blue area, notice that again, it's being illuminated with white light, all the different colors. Most of them are being absorbed with the exception of blue being sent in the direction of the camera. If that was kind of confusing the first time, let me try to illustrate this. I'm going to illustrate with just a few of the colors of the rainbow. You know, obviously, when white light hits this black paper, all the colors are hitting it, but I'm not going to do Roy G. Biv. I'm just going to show you the green, the blue, and the red. But if this was truly a black piece of paper, nothing would reflect. We would see the blackness of space, but that's not what's really happening. We're seeing a small amount of the green, a small amount of the red, a small amount of the blue being reflected. That's why we see something when we look at the paper. It's kind of a dull gray. More importantly, let's focus on what's happening when the white light, all the colors, hit the red test. It's the red part. Everything else gets absorbed with the exception of the red. The red gets reflected off of the red crayon. That's why it looks red. And likewise, in a similar way, all the colors hit the blue test written area of crayon, but only the blue bounces off the crayon and winds up in the camera. That's why it looks blue. And it's a similar story over here with my white paper. The difference being, with white paper, the areas of white are reflecting all the different colors. They're being illuminated with all the different colors, and they are reflecting all those colors. So we are seeing most of the paper as being white, with the exception of those two areas. Okay, so I'm not going to draw all the colors of the rainbow, but when you're looking at the white paper, you're seeing essentially all the colors: red, orange, yellow, green, blue, indigo, violet, and they are bouncing back into your eye. When you're looking at the white part. And when you're looking at the red part, you're you're seeing the same thing, except what's happening is the red is hitting the crayon and bouncing back. It's not being absorbed, it's being reflected. Likewise with the blue part. All the colors are being absorbed with the exception of that particular color. That's what winds up coming into the camera, or at least that's what winds up arriving at the filter. And we'll talk next about what happens when you put the filter in between your paper and the camera. Now, let's see what happens when we put different color filters in front of my camera lens. So I'm going to put first a blue filter in front. And notice what happens. What do you see? Now, before we address the writing part, let's just talk about why this black construction paper appears to be blue now. Remember, we said it wasn't perfectly black. In fact, we said that of all the visible light that was hitting the paper, a small amount of all the colors, I'm just going to draw red, green, and blue here, but all of the visible colors are being reflected in a small amount from this supposedly black piece of paper. Remember what a filter does. A filter only allows a light of a particular color to pass through. So of that visible light that is coming back from the piece of paper toward the filter, the only one that's going to get through is the blue. The red and the green and the yellow and all that other stuff is going to get blocked by the filter. The blue will pass through, and that's why this supposedly black piece of paper appears to be blue through our blue filter. It's because only the little bit of blue light that's being bounced off of the paper is actually getting through our filter. Okay, now if you're like me, and I know I am, I actually see a little bit of writing up top there. Does it look red? No, it doesn't look red, and we'll explain why here in a second. But first of all, let's think about what's happening. As we just mentioned, in the paper areas, just the blank paper, a small amount of all the different visible wavelengths are being reflected from that paper because it's not perfectly black. And we have a filter in place, and so therefore only the blue gets through, and that's why the paper looks blue. Now what's happening in the crayon areas? Remember, the crayon was red, and therefore it's going to absorb all the lights, all the colors of light, with the exception of the red is coming toward the filter. However, what kind of filter is this? It's a blue filter. Blue filters only allow blue light to pass. So therefore the red light that's coming from the crayon toward the camera is being filtered out by the filter. So what are we seeing? We don't see a red test. We only see a test that has a little less light information than the rest of the paper. Okay, so now we understand why we are able to see test up top. Again, it doesn't look red, it just looks kind of dark, and that's because we're getting no light information because the red light is being filtered out, and so we're getting no light for those little test areas. We're getting some blue light around it, so we're getting some contrast. Now what's going on down below? Why are we not seeing the test down here? Remember, that was written in blue crayon. So what's happening for those blue crayon areas? A little bit of blue is being returned toward the filter, but of course, remember what's happening around it. We also have blue light and red light and green light being returned just off of the blank paper. When we put the filter in place, of course, it blocks out the green light, the red light. It allows the blue to pass, but notice we have no contrast. Yes, the blue is passing through from the crayon, but it's also passing through from the surrounding blank paper, and therefore there's no contrast for us to see that test message. Now, I'm going to put a red filter in front. What do you see? So the first thing I want you to ask yourself is, why the heck is this black paper red? Remember, this is not perfectly black paper, so it is reflecting a small amount of all these different colors. Again, all the different colors of visible light. I'm only drawing red, green, and blue right here. But again, Roy G. Biv is being bounced off the paper in small amounts. It's not a perfectly black piece of paper. If it was truly black, nothing would reflect. We would see essentially an absence of light. We are seeing a small amount of light. We've got a red filter now in place, which means that the blues can't pass, the greens can't pass. That's why this supposedly black piece of paper appears to be red. Okay, so we see a red piece of paper. What else do we see? We also see test written down here at the bottom. What color is it written in? Well, I don't know. It looks just dark to me. It doesn't look like any particular color. It seems like it's an absence of light. Well, that is correct, because what's happening? The actual color, remember the crayon was blue down here. And so the blue crayon is reflecting, it's absorbing all of the colors except for it is returning blue toward the filter. But what kind of a filter are we talking about? We're talking about a red filter. So that blue light coming from the crayon can't pass through the filter to get into the camera. So therefore, in those crayon written areas, we're actually getting no information compared to a small amount of red light around the crayon written areas. So therefore, we have some contrast. That's why you see the word test written at the bottom. And finally up top, what are we seeing? We're seeing shinola, essentially. There should be the word test up there, but I'm not seeing it. Why is that? Because it was written in red crayon. So the red crayon area is what was going on there. They were absorbing all light except for a small amount of red being bounced back toward the filter. What does the red filter do? It allows red to pass. So we are getting red light from those crayon areas. But what are we also getting? We're getting the red light from the plain black paper areas, and therefore we have no contrast. We're getting red light from the crayon areas, but also red light from the areas surrounding the crayon areas, and therefore there's no contrast, and therefore we can't see the word test. Now let's go over to the white paper. And we'll do the same thing. Again, here's what it looks like unfiltered. And again, think about why you are seeing what you are seeing. Now let me put a blue filter in front. So first ask yourself, why is the white paper blue? Are you asking yourself? Really? I mean, ask yourself, why is the white paper blue? Remember, the white paper reflects, it's white, so it's reflecting all the different colors of light, red, blue, violet, etc., etc., Roy G. Biv. So all this light is coming toward the filter. What kind of a filter is it? It's a blue filter. So therefore, it's going to filter out the red, the green, the yellow, the orange, etc. The only one that's going to pass through is the blue. That is why this white paper appears to be blue. Now we see two tests, don't we? Let's tackle the bottom one first. Now notice neither of them is actually a particular color. They both just kind of look dark. The question is, okay, why is the bottom one fainter than the top one? Remember, the bottom one is written in blue crayon. So notice what's happening. The white light is hitting that blue crayon. All of the colors are being absorbed with the exception of the blue. But remember, around the crayon written areas is white paper, which is reflecting blue as well. So through this blue filter, I'm getting a lot of blue information. There's not as much contrast. I'm getting blue from the paper. I'm getting blue from the crayon itself. And so therefore, I'm getting a little less blue from the crayon than I am from the paper, and therefore it appears to be slightly darker. So I have a little bit of contrast, but it's not that much darker or that much dimmer, and therefore it looks kind of light in this picture. And finally, the top test. Remember, that was written in red. It doesn't really look red here. Well, why is that? It just looks dark. What is dark? Dark is an absence of light, an absence of or lack of information. Well, why is that? Because we have red light that is being reflected off of that red crayon. But remember, it's trying to go through a blue filter, and therefore the blue filter doesn't let it pass. So essentially we have an area where there's no light coming from the crayon, as opposed to from the paper around the crayon areas, we're getting some blue light passing through. Therefore we have more contrast in the top written test than on the bottom written test. That's why the top one is easier to read than the bottom one. Now, let me put a red filter in front. At this point, it should be very clear why you are seeing what you are seeing. Why is the paper red? Well, it's white paper. That means it reflects all the colors of light, red, green, and blue. We've got a red filter, and of course all the other visible colors of light. Of course we've got a red filter, which means that we only see the red passing through. That's why the paper appears white. Why do we only see the bottom test? Because it was written in blue, remember. So the light that's coming off of that crayon is just blue. What happens when it encounters a red filter? It gets blocked out. So what are we left with? We're left with the white, the red that's coming from the paper around it. On the top, why are we seeing no test up there? Because it's red light being returned from the crayon, but we're also getting red light from the paper around, therefore no contrast, and therefore we don't see the word test. Pretty cool. Color filters. Awesome. Okay, now we're going to explore what's called refraction, the fact that light does not always travel in a straight line depending upon the medium that it is moving through. So we've got light that's traveling through air, and then it encounters a block here. This is actually some sort of a plastic or an acrylic block. And you can see that the light does indeed bend, both going from air into the acrylic, but also then coming from the acrylic back into the air. Notice there's actually two bends. I'm going to turn off the light and you can see that a little bit better. Again, the light does not travel in a perfectly straight line. It actually refracts. It bends as it encounters the plastic. As another example of refraction, what I've got again is an acrylic block, but this time it's a semicircular shape with a flat side and then a circular side. And notice that my light source is pointed straight at the flat side. And we can see that the light passes through the block and essentially moves in a straight line. But what if I change the position of my light source so that it is now coming in at an angle? Notice that we get bending. The light bends as it moves into the block as well as when it exits the block, going from the plastic back into the air. So we see that the light bends toward the normal as it moves from air into the plastic, and then it moves away from the normal as it goes from the plastic back into the air. Okay, so we've already been talking about refraction, the fact that light does tend to bend or change its direction when it moves from one medium to another. But it turns out that light is made up of, what we think about as visible light, is made up of a bunch of different colors. And different colors, different frequencies of light do not bend in equal amounts. And we can actually see that more dramatically when I turn the light off here. So I've got my light source, single beam going into my acrylic block. And notice what happens. That light, get it as close as I can here, does not bend equally. Notice that the reds bend a little bit less than the blue end of the spectrum. So we're able to break up that white light into its component colors: red, orange, yellow, green, blue, and violet. Roy G. Biv. That's what we call dispersion. Okay, so now we're going to talk about how the eye sees what it sees. And in order to do that, we're going to use our acrylic glass block, or acrylic block, semicircular. That's going to act like the lens in your eye. And of course we have the light source. And so we're first going to see how the eye works when you're looking at an object that's pretty far away. And when an object is pretty far away, the light rays that are arriving are essentially parallel to each other. And notice what the lens then does. It focuses the light down to a point. Again, so we're making a model of the human eye and how you see with normal vision. And we're looking at a distant object, and therefore we're going to treat the light that's coming into the eye as being essentially parallel rays of light. And that light then is focused by the retina, or I'm sorry, by the lens, down to a point. And it turns out that for normal vision, the retina is the distance of the focal length. If the eye is relaxed, it's not thickened. It turns out the eye muscle can thicken the lens. But right now we're dealing with a relaxed eye, and sure enough, it focuses the light down to a point, and that point, the distance of that point, is the distance of the retina. So now what I've done is I've changed the light source. Notice that the light isn't, these are not parallel rays, rather they're kind of diverging rays. And that's from that would be if you had an object that is closer. So your light is not going to be parallel, arriving at the eye. The light's going to be kind of in kind of divergent rays. And notice that the lens does focus that light, but the focal point winds up changing. And your eye has to accommodate for that. Okay, so I've left the drawing up from the faraway object just to show you the difference now, because now we're dealing with a nearby object. And so the nearby object means that we're going to have rays that are not parallel, but rather they're sort of divergent when they hit the lens of the eye. And notice then that the lens, I'm just swapping out my colors here. I'm going to make my focus light now red. And notice that now we see that the lens tries to focus the light down, but it can't focus it to the same plane that it did before. The focal point now is longer, which means that the light that is hitting remember the retina is the blue here. That's the retina. And so therefore, when we have a nearby object, despite the attempt by the lens, it's unable to focus the light at the retina without making some changes. So now what I've done is I've taken my divergent light source and I've put an extra lens in front of my semicircular acrylic block. I've got a convex lens here. And notice what that does as far as changing the focal point of my light. So remember that a nearby object was caused with the divergent light from a nearby object. We were having a problem getting the lens to focus the light at the retina. But notice what we've done with this particular image. Now we have added an extra lens. We put a little convex lens in front. This is essentially to mimic what the eye does to accommodate for nearby objects. It essentially changes the shape of the lens. It thickens it a little bit. And by thickening it, notice what happens. Now we're able to focus the light where it needs to be, essentially at the retina. So that's what the normal eye does in dealing with nearby objects. It thickens the lens and therefore is able to focus the light to the retina.
Okay, so to finally kind of wrap things up for this light module, I wanted you to take notice of an activity. This is actually described on page 293 of your book about the blind spot of the human eye. You have been reading all this stuff, right? You do want to learn this stuff, right? Okay, well, if you haven't checked this out, again, you can do this either with this screen or check out the book's more elaborate description and explanation. What you can do is close your left eye and look at the dot on your screen. Focus on the dot and then move. Now, of course, you can't move your screen. Well, I guess you can if you're looking at this through using a phone. But for me, I have to move my eye toward the screen. And if I'm really focusing on the dot, there's a point right here where I can't see that X, because the X is now, the light from that X is being focused on the blind spot of my eye. So if anybody ever tells you how wonderful the human eye is, what a magnificent creation it is, if you haven't learned by now in this module, the human eye stinks. It's really a lousy device. Not only can we not see stuff outside of this really little sliver, tiny little sliver of light, there's so much else that's happening, and yet we can only receive a small section of all that is happening. We only see the visible spectrum of light through our eyes. But even that little bit of light that comes that we're able to actually see, it turns out, because of the way the eye is wired, we actually have a blind spot, a place where all the nerve endings connect, and there's no receptors at that position. So that's not exactly the most wonderful design in the world. But anyway, I hope that kind of ties together all this stuff about light, that you now understand more about the electromagnetic spectrum, and that you now understand what happens to light when it passes through other media like glass and water and all that kind of stuff. Hope you've enjoyed it.